Okay, so good morning, guys. So today we're going to start with the third module in our studies, and this third module is on the stability and stability measuring techniques. You can see it will be on chapter 6 of the Norman S. Neese textbook. So what I'm going to do is that I'm going to give us this first class is going to be divided into two videos. The first one giving us an introduction to how do you define stability in control systems, and then we go on to how do we determine if a system is indeed stable. So stability, that's what we are trying to learn. Now if you remember from unit 1, we said one of the design objectives of control systems is to ensure that a system is stable, right? So we're going to look at two methods of determining the stability of a system. The first one is a analytical method, whereby you're analyzing the transfer function of a system, and the second one is a diagrammatic or a plot method, where we are going to plot the system on MATLAB, and we're going to analyze it based on the plot data. So without further ado, let's start. Now, in this figure, we can see here that we have defined what is the three forms of stability that a system can encounter. Now, you have a stable system, you have an unstable system, and you have something that is called a marginally stable system. So these are very much linked to the damping ratio of the system that we learned in module 2, and also with regards to the natural response and the forced response of a system. So if you remember, we had a discussion where we said that the stability of a system is equal to the forced response of the system plus the natural response. So this is something that we discussed, right? So every system will have a forced response and a natural response within it. Now, a linear time invariant system is said to be stable if the natural response approaches zero as time approaches infinity. So if you take this graph here for the stable system, you will see that this is the time axis and this is the amplitude. So for a time invariant system to be stable, the natural response should approach zero as the time approaches infinity. So this is a stable system. It will have an initial rise, then these rises will die down and finally settle at a zero value as time approaches infinity. Okay. Now an unstable system. This is a linear time invariant system where the output is growing with the increase in time. Okay. So you can see here it's starting out to be small, but then as time goes on, it becomes greater and greater. So that is an unstable system. Then you have a marginally stable system. So with a marginally stable system, what happens is that the system never dies, nor does it rise. So you can see that it is an oscillation. So it goes to a high, comes to a low, goes back to the high, and it keeps moving in that direction. So that is called a marginally stable system. So we can also link the stability of a system with respect to the location of the poles of the system. So if you're having a stable system, you will see that all the poles must be on the left-hand plane. So where is the left-hand plane? So here we have a S-plane diagram. You have the left-hand plane on this side, and then you have the right-hand plane on this side. So for your system to be stable, all your poles should be on the left-hand plane. Now if a system is unstable, then one or more than one pole will be on the right-hand plane. So you can have a situation where there are poles lying on the left-hand plane, but if there is even a single pole lying on the right-hand plane, it would mean that the system is unstable. So poles located on the right-hand plane point to an unstable system. And if you are having a marginally stable system, you'll see that for that kind of a system, the poles will lie on the j omega axis, that is this axis that we have. All the poles will be lying on the j omega axis. There you can see the definition of a marginally stable system. If the natural response neither decays nor grows but remains constant or oscillates as time approaches infinity. So this is referred to as your marginally stable system. Now you can also define stability in terms of a concept called BIBO or BIBO. So BIBO basically stands for bounded input, bounded output. That means if you have provided a bounded input to your system, you should expect a output which is within the boundaries. So if a system is stable, if the natural response approaches zero as time approaches infinity, a system is unstable if the natural response approaches infinity as time approaches infinity. If the system is marginally stable, the natural response neither decays nor grows. So when you put it into BIBO, a stable system, for every bounded input, there should be a bounded output. For an unstable system, for every bounded input, there is an unbounded output. So this is how we measure that. Now, I said earlier that the location of the poles play a role in the stability of the system. So let's put that to measure. So what we've done here is that we have taken an open loop transfer function 3 divided by s into s plus 1 into s plus 2. And as you can see here, it is provided with a step input and it is given into a feedback system. Now, you can see that this is a third order system because there are 3 poles at the denominator, right? Now, what they have done is they have taken the roots of this equation. So if you use your calculator, you can find out what are the roots of this equation. So you first need to multiply this out. So this becomes s square plus 2s plus 2 into s. So if you take the roots of this equation, you will see that it has 3 poles. The first pole is lying at minus 2.672 and the other 2 poles are lying at minus 0,164 plus or minus 1,047j. So this is something that you guys can try and do on your calculator. So it's the roots function in your calculator and you can do that. Otherwise, if you have access to MATLAB on-ramp, you will see that you can plot this on your MATLAB and you will see how that works. In our next video, I'll show you an example of what needs to be done for you to do this on MATLAB. But in any case, by simply finding the roots, you will see that all the roots are lying on the left-hand plane. And naturally, we said that if the poles are lying on the left-hand plane, then the system is said to be stable. And this is the kind of response that you get. So here, 1 is the ideal response that this system should end up with. And you can see that as time grows, the response initially has a peak, but then those peaks die down and it finally settles down at this value. So it is in agreement with that statement where it says that the output approaches 0 as time approaches infinity. All right. Now let's consider another example. Again, a third order system. The open loop transfer function is 7 divided by s into s plus 1 into s plus 2. Once again, you can calculate the roots of this equation using your calculator. Find out what is the denominator, multiply it out, and then calculate the roots of the equation. Now, when you calculate the roots, you'll see that one pole is lying on the left-hand plane at minus 3,087. And the other 2 poles are lying at 0,0434 plus or minus 1,505j. Which means that one pole is lying on the left-hand plane and 2 poles are lying on the right-hand plane. Once again, if you plot this on MATLAB, you will see that this is the kind of graph that you'll be getting. So your output should stabilize at 1 if it is a stable system, but you can see is that as time approaches infinity, this system is actually growing. Therefore, the system is said to be unstable. Okay. So what we're going to do is we're going to see how we can determine if a system is stable or not. And for this purpose, we're going to use a technique called the Routh Huwritz criterion. So the Routh Huwritz criterion is provided in your textbook. This is what it's called. It's the Routh Huwritz criterion. So in this method, there are some steps that we need to take, right? So the first step is to create the Routh table. And then you apply what is called Cramer's rule in mathematics, and then you're going to find the equation. Right, so let us take it step by step. The first thing that I want us to do here is I want us to try and see if we can find the closed loop transfer function. So the most important thing when we are doing the Routh Huwritz criterion is that we need to find the closed loop transfer function. So here's a question that is given to us, whereby the open loop transfer function is 1000 divided by s plus 2 into s plus 3 into s plus 5. So before we use the Routh Huwritz criterion, the most important thing we need to do is to find the closed loop transfer function. So the closed loop transfer function is something that you will be familiar with when you are doing your lab sessions. That will be this week. But for those who are not conversant with it, it's very easy to calculate on a piece of paper as well. So what you do is you look at what is the feedback that is provided in this system. So you can see here that the output is fed back to the input, and it is a unity feedback. So the unity feedback is the one that is going back to the error signal. So your G of s is 1000 divided by s plus 2 into s plus 3 into s plus 5. Now to calculate the closed loop transfer function, the equation is such. It is G of s, which is already given here, divided by 1 plus G of s into h of s. In this case, h of s is the feedback, and it is a unity feedback, which means that it is equal to 1. Therefore, your equation basically becomes 1000 divided by s plus 2 into s plus 3 into s plus 5, the whole divided by 1 plus 1000 divided by s plus 2 into s plus 3 into s plus 5 into 1. Right? Therefore, when you cross multiply, you will see that the denominators will get cancelled, and you will be ending up with 1000 divided by s plus 2 into s plus 3 into s plus 5 plus 1000. So this is something that you can try. And when you do the calculations, you will see that you will get you have reduced the block, you have got rid of the feedback loop, and you end up with the input, the output, and the closed loop transfer function, which is 1000 divided by s cube plus 10s squared plus 31s plus 1030. Right. So you can see what we've done here. I've done is that I've gone back to this problem, and I've actually calculated the closed loop transfer function in each of these cases. I'll upload these notes so that you can also follow them, but it's quite simple. I've taken G of s, which is 3 divided by s into s plus 1 into s plus 2, divided by 1 plus 3 into G of s into 1, which is the unity feedback. And then I get this equation at the denominator. Now if I take the roots of the closed loop transfer function, that is this denominator on the calculator, like I mentioned, you get minus 2.67, it should be 2.67 here, comma 0.16 plus or minus 1.05 j. Right. So this is how we get to that plot here. We can do the same for the second one, right? So what are the conclusions? If the closed loop poles lie on the left-hand plane, the system is stable. While if the closed loop poles lie on the right-hand plane, the system is unstable. So how do we now do the Routh Huwritz criterion? So step 1 was to find or determine the characteristic equation. So what is the characteristic equation? it is the denominator of the closed loop transfer function. So you need to find T of S, and then the denominator of T of S, that is this portion here, that is your characteristic equation. So it's very important that we find out what is the characteristic equation. Okay, so like I've stated here, the characteristic equation is the denominator of the closed loop transfer function. And once you have identified the characteristic equation, what we do is we go to step 2, which is to create the Routh table. So we identify the terms that define this characteristic equation. It's s cubed, s squared, s, and s raised to 0. So we write those vertically. So it's s cubed, s squared, s raised to 1, and s raised to 0. Now the third step is to do what is called the populating of the Routh table. So what happens here is that you write them alternatively. So on the s cube row, you write all the odd coefficients. So the odd coefficients are the coefficients of s cube, s in this case. So the coefficient of s cube is 1. The coefficient of s is 31. Right? Now in the second row, you have the coefficients of your even row. So in the even row, it is s squared and s raised to 0. So there you will see that it will be 10 and 1030. Now one of the good things about the Routh table is that if there is a common denominator that you can use to divide throughout to make a Routh table simpler, then you can do so. In this case, you can see that you can divide throughout by 10. So what I've done is that I've divided s squared row throughout by 10. Therefore, I end up getting 1 and 103. So this is how we populate the s cube and s squared row. But now we need to find out what is s raised to 1 and s raised to 0, right? So the challenge that we have is we need to use what is called the Cramer's rule. So I'm going back to explain to you how the Cramer's rule works. So in the Cramer's rule, if you have a determinant which is a, b, c, and d, right, by virtue of the Cramer's rule, to find the value of the determinant, the formula is b into c minus a into d divided by c. So it's b into c minus a into d divided by c. Okay. So now what I've done is I've taken these terms that are available in our Routh table and brought them into this determinant formula. So you can see that in this Routh table, I have 1, 31, 1, and 103. So I'm going to solve this using the Cramer's rule to get the value for s raised to 1. So I brought it here. It is 1, 31, 1, and 103. So by virtue of the formula, it is b into c. So it is 31 into 1, which is 31, minus a into d, which is 1 into 103, which is 103. So 31 minus 103 divided by 1, which is equal to minus 72. So therefore, I get s raised to 1, which is minus 72. Now to calculate the second cell of s raised to 1, I again use the Cramer's rule. But this time, the difference is that it's going to be, let's call it b. So the cells that populate that value are 1, 1, 0, and 0. So it goes from side to side. So if you want to find the first cell of s raised to 1, it will be 1, 31, 1, 103. But now if you want to find the second cell, which I have called as b here, it will be 1, then the row here, which is 0, 1, and the row here, which is 0. So it will be 1, 0, 1, 0. And when you multiply and use the Cramer's rule, you will find that that is equal to 0. Okay, so we have now got s cubed, s squared and s raised to 1, and we are left with finding s raised to 0. So how do we find s raised to 0? So we write all the values that make up the first cell of s raised to 0. I'm going to call it C. So over here it will be 1, 103, minus 72 and 0. So the formula that we have is B into C, which is 103 into minus 72 minus A into D, which is 0, the whole divided by minus 72. So it will be 103 into minus 72 divided by minus 72, which will be 103. Therefore, I get this value of 103 at the first cell of s raised to 0. Then in the second cell of s raised to 0, we do it by writing down the values that determine this one. So it will be 1, 0, minus 72, 0. When you calculate that, you get it as 0 minus 0 divided by minus 72, which is 0. So in doing, we have created the Routh table. So I want you to take your time and try and do this very same example to see if you understand. Now we go on to the analysis using the Routh Huwritz criterion. That is the third step. So the Routh Huwritz criterion states that if there are sign changes in the first column of your Routh table, so we are only looking at the first column, right? So this is the first column, this entire row here. So if there are sign changes in the first column of the Routh table, that indicates that there are poles lying on the right hand plane. So if there's any poles lying on the right hand plane, there will be sign changes. So if you have a look here, from s cubed to s squared, there are no sign changes. It's positive to positive. But when you go from s squared to s raised to 1, you go from 101 to minus 72, which means that there is a sign change. And when you go from s raised to 1 to s raised to 0, again, you're going from minus 72 to plus 103. So there are two sign changes. And the number of sign changes is equal to the number of poles lying on the right hand plane. So in this case, in total, you have 3 poles because this is a third order system. And out of those 3 poles, 2 of them are lying on the right hand plane. Therefore, the system is said to be unstable. Okay. So this is an example that I want us to try. It is called making the Routh table and tell how many of the roots of the following polynomial lie on the right hand plane and the left hand plane. So this is the equation that is given there. It is 3s raised to 7 plus 9s raised to 6 plus 6s raised to 5 plus 4s raised to 4 plus 7s cubed plus 8s squared plus 2s plus 6. So you can see here, for simplicity, they have given us the characteristic equation. So we do not need to find the closed loop transfer function here, but rather we can go straight into finding what is use the characteristic equation. So you can see here that the table is populated. I want you to do it on your own. In our next class, we'll start by discussing this one and then getting it forward. But then try and see if you are getting the exact values that I've got here. And we will start with explaining those. So once again, to recap, the steps used in the Routh Huwritz criterion, right? So let's discuss those. We first need to find the closed loop transfer function T of s. If T of s is given, we need to choose the denominator. That's how we did our first problem. The second problem that I asked you to try, you're already given the characteristic equation, so you can start with that one. Then we create the Routh table. After that, we populate from the very top row to the very last row, the Routh table. Then we analyze the first column to see how many sign changes are there. If there are any sign changes, that means that there are poles lying on the right hand plane. So I want you to give this one a try, and I want you to see if you can get it. In our next class, we'll start with discussions on this, And we will also look at special cases for the Routh Huwritz criterion. There are two of them. It is a 0 in the first column, and also you have another case where there is a entire row which is filled with 0, which is what we will be discussing also, right? So there will be two, yes, here it is, entire row being 0. So have a look at the section till here, that is solving that equation that we have, and try and apply these rules that we have here. The notes for this section will also be provided. Good luck.